Sorry to keep everyone waiting. I got halfway here before I realized I'd forgotten this. This is the envelope of ISIS forms. I'll say more about this in about 50 minutes, but there they are. Okay, so this is the last lecture of the semester. The stuff that I'm talking about in this lecture is not going to show up on the final exam, but nevertheless, I think it's the topic I'm going to talk about connects to things we've been doing recently to some stuff that we did earlier in the semester, specifically using linear programming and using randomization as a tool to develop approximation algorithms. If I'd had one more lecture planned into the semester, I might have also talked about using dynamic programming as a tool to build approximation algorithms. But there's only so much time. So let me remind you where we're standing, the kinds of things that we're talking about. Approximation algorithm, the goal is, given some instance x, I want to compute some solution a of x to some fixed problem. So maybe x is a weighted graph, and a of x is the some short Hamiltonian cycle in this graph. Or say x is a collection of jobs and a of x is a schedule. And I want to do this in a way such that the quality of the solution that I compute is guaranteed to be within a certain fraction, a certain constant, or a certain, let's say, just a certain multiple of the optimum solution for that particular instance. So on Tuesday, I showed an algorithm based on minimum spanning trees, for example, that computes given a graph with weighted edges that satisfy the triangle inequality. I can compute a Hamiltonian cycle, a of x, that is at most twice as long as the shortest Hamiltonian cycle. So the ratio between the cycle I compute, a of x, and the optimum cycle, opt of x, is at most 2. Right? I also talked about this the very natural greedy algorithm for vertex cover, where given an arbitrary graph, I can compute a vertex cover that is guaranteed to have at most a factor of big O of log n more vertices than the smallest vertex cover. So in that particular case, this approximation ratio is actually also a function of the input. So typical things you're shooting for here, maybe this is 2. Maybe this is log of the size of the input, what we normally represent as n. Maybe it's something like square root of n. Depending on which NP-hard problem you're talking about, we have varying abilities to actually compute approximate solutions in polynomial time. Okay. So, one tool that actually proves to be incredibly useful in practice for not only actually designing approximation algorithms, but designing exact algorithms that are fast in practice, although we aren't necessarily going to be able to prove that using the tools we've seen in this class, is what's called integer linear programming. Now, we've already seen linear programming, so I'm adding this adjective here, integer linear programming. And if you recall the standard canonical form of a linear program is something that looks like this. So I have an unknown vector x that I want to compute, and I want to compute the best possible vector where the value of a vector is its dot product with some other vector c that I know that's encoded in the problem, subject to a bunch of linear inequalities, which with a little bit of symbol manipulation I can always rewrite into the form that if I take this matrix A, which again is defined by the problem, and compute its product with the vector x, I get another vector. And component by component, that product vector must be less than some vector b, which is again fixed by the problem. And moreover, each of the variables in the vector that I'm trying to compute must be non-negative. Okay, so this is a linear program in canonical form. If I want to make this an integer program, I will add one more constraint, which is that each of these d coordinates, this d-dimensional vector, must be integers. Okay. Now, if you recall when we were talking about flows, the maximum flow problem you can cast as a linear programming problem, right? You want to maximize the total amount of flow out. So for every edge leading out of the source vertex, you have a coefficient of 1. For every edge leading into the source vertex, you have a coefficient of -1. And then these constraints say things like the flow across an edge must be non-negative, the flow across an edge must be less than its capacity, and the flow into any vertex must be equal to the flow out, unless that vertex is S or T. Those can all be incorporated into this system of linear inequalities. But we showed when we were thinking about the Ford-Fulkerson algorithm that if all of the capacities are integers, then the flow value you get out from the maximum from the Ford-Fulkerson algorithm, all the flow values are integers. Now, in the maximum flow linear program, the objective vector, every coefficient here is either 0, 1, or -1. It's always an integer. And it turns out that all of the coefficients inside this matrix A are also either 0, 1, or -1. So for that particular linear program, is the coefficients over here on the right, these are the edge capacities. And what we showed is, as long as those edge capacities are integers, the maximum flow you get is an integer. And so for that linear program, adding these integer constraints doesn't do anything, right? But in general, that's not going to be true, right? So I want you to imagine that this grid, which I normally write against and normally ask you to ignore, I'm now actually going to ask you to notice. There's a grid on the screen. This is graph paper that I'm drawing on. So I can define, if you want to imagine some sort of two-dimensional linear program. And I might, in this case, if I were looking for, say, the lowest point inside this polygon, then the point that I would look for is this one down here. But if I'm restricted to looking at the integer points, namely these things that I'm pointing out here in pink, then the best one I can get is, say, this one. So in general, the optimal solution to a linear program is not going to be all integers. It's very easy to write down concrete examples where this is the case, and I'll see a couple of those. But there might still be an optimal integer solution sitting inside this feasible region. Okay. Now, as a general rule, integer linear programming is NP-hard. Now again, there are special cases that are not NP-hard. One of them is maximum flows. But in practice, there are often very good integer programming solvers that can quickly converge most of the time in practice to the optimal solution here. But in general, this is NP-hard. And, so I'm going to ask you to prove that this is NP-hard right now. So here's the proof. Reduction from what? This doesn't look like any of the problems that we've seen before, and so what should we try? 3-sat. Good. Okay, why not? Okay, so I'm given a formula which consists of clauses ANDed together. Each clause consists of 3 literals ORed together, and each literal is either variable or its complement. So just as an example, A or B or C, and A bar or C or E bar, and so on. Okay. So I'm given some arbitrary 3-sat formula, and I want to turn it into some kind of integer linear programming problem. Yeah.
A bit is an integer between 0 and 1.
Right, so a bit is an integer between 0 and 1. So what I'm going to do is I'm going to set up a variable inside my integer programming problem for every variable inside my Boolean formula. And instead of having true or false, which is the values for Boolean formulas, I'm going to use the entirely different values 1 and 0, where, like a good computer scientist, 1 represents true and 0 represents false. Please do not ever make the mistake of assuming that 1 is true. They're different types, so they're different values. But in any case, I'm going to assume, I'm going to map this Boolean variable A onto an integer variable, which I'm going to conveniently call A. Now, there's another convenient notation which electrical engineers tend to like, which uses plus to mean or, and times, or just concatenation to mean and. And this almost gives the game away. I need to find integer values, either 0 or 1 for A, B, and C, such that at least one of these values is equal to 1. How do I write that down? Yeah, so A plus B plus C is at least 1. What do I do for A bar plus C plus D bar? Right, so not is the same as 1 minus. So I'm going to write down 1 minus A plus C plus 1 minus D is at least 1. Or if I really want to be nice, I could, do some math. Okay. And so what I'm asking then is, for each clause, I get a linear inequality. And then at the bottom, I'm going to say, A, B, C, etc. are all less than or equal to 1 and greater than or equal to 0, and they're all integers. And what I have here now is an integer linear program, which is feasible if and only if the original 3CNF formula is satisfiable. And any program which can compute the optimal solution to an integer program has to be able to tell you at a minimum whether the integer program is feasible or not. Okay, so basically I get an argument that this is satisfiable if and only if this corresponding integer program is feasible. Okay. Now I do want to point out something weird about this integer programming problem, which is, okay, so that's proof that it's NP hard. But now think about this linear program. No integer constraints. I claim that this linear program is always feasible.
You said everything that have on the left-hand side is always 1.5.
Right. So I set every variable to be equal to 1/2. And then every single left-hand side of this inequality is 1/2 plus 1/2 plus 1/2 is at least 1. Hooray! If every variable is halfway between true and false, then every clause is satisfied, and we're done. So this linear program is called the linear relaxation of the complete integer program. In this particular case, it's really kind of useless. It's like, okay, don't decide between true or false. I get somewhere in between. Okay, but I'll show you another case where the relaxation doesn't tell you anything directly, but it tells you something just one step off from something useful. Okay, so that particular problem is minimum vertex cover. All right, so again, we've seen this several times already. The input is an undirected graph G, and the output is the minimum number of vertices in some set C, such that for all edges, either U is in C or V is in C. All right, so I want to choose the smallest subset of the vertices that I can that touch every edge, or that cover every edge. Okay? So now that I've proved that integer, okay. Let's prove once again that theorem, integer linear programming is NP hard. Proof. I'm going to describe a reduction from minimum vertex cover. We already did 3SAT. Let's do minimum vertex cover. So the choices that I need to make to solve the minimum vertex cover problem is for each vertex in the graph, do I add it to my cover or not? And I'm going, my variables are going to correspond to vertices in the input graph. Okay. So I'll write x sub v for the vertex v. Okay, great. And in particular, x of v equals 1 corresponds to vertex v is inside the cover. So if I want to minimize the number of vertices in the cover, then my objective function is just the sum over all v of these indicator variables. I do want to write that these are indicator variables. This is, of course, shorthand for every xv is greater than or equal to 0, every xv is less than or equal to 1, and every xv is an integer. And now I need an intermediate thing that somehow encodes that these indicator variables describe a vertex cover. So what should I put there?
For every edge, the sum of the variables is greater than equal.
That's it. XU plus XV is at least 1 for every edge UV. Okay, and it's hopefully easy to see that this integer linear program correctly encodes the minimum vertex cover problem. It's a binary choice because of the constraint at the bottom. It's a vertex cover because of the constraint in the middle, and it's a minimum vertex cover because of the objective function at the top. And so again, we've proved that integer linear programming is NP-hard. Okay. So again, there's something interesting that happens if I relax this to a linear program. So the linear relaxation, instead of saying every XV is either 0 or 1, is the natural thing to do is to say every XV is between 0 and 1. Again, this LP is always feasible because I can just set every one of these variables to be 1/2. And then for every edge, 1/2 plus 1/2 is at least 1. Actually, I knew it was already going to be feasible because I could just set all the variables equal to 1. But I can, what this says is that I can get a feasible value less than or equal to n over 2 because I know I can get n over 2. N over 2 vertices by having half of each vertex. Okay, so let me write opt to be the size of the minimum vertex cover. And I'm going to write opt with a twiddle over it to be the solution to the LP relaxation. This is relaxation. This is sometimes called the optimal fractional solution because it's not necessarily an integer. Now the first thing to notice is opt is greater than or equal to opt twiddle. The art of designing an approximation algorithm when you're trying to minimize things, the key thing that you want to be able to do is to be able to prove some kind of lower bound on the optimum solution. You need to be able to argue that the optimum solution is bigger than something, and that something is bigger than what my algorithm actually does somehow. Okay. Now, I can solve this linear program in polynomial time because I can solve any linear program in polynomial time. And it's going to give me something better than the optimum vertex cover. The problem is that the thing that it gives me isn't a vertex cover. It's some collection of fractions whose sum is guaranteed to be less than or equal to the size of the optimum vertex cover. So somehow I need to take this fractional solution and turn it into an integer solution. So what I'm going to do is I'm going to round, right? So I'm going to define x prime of v to be 1 if the optimum, the x star here is the vector, the optimum, not the value of the optimum solution, but the actual location of the optimum solution, the values of those variables, is at least 1/2, and 0 if the optimum variable for vertex v is less than 1/2. So I'm just going to take round it to the nearest integer, and following the rule that you learned in 4th grade, always round 1/2 up. Okay? So one of the simplest possible things you can do. So, all right, now there are 2 claims. X prime describes a vertex cover. Why's that? Now, x prime is a bunch of zeros and ones. And what that means is if I take the set of vertices whose x prime variables are equal to 1, that set of vertices covers every edge. Yeah?
So you never round 2 down because then they would both be less than 1.
Yeah,
You
so
never both ends down.
if I look at the vertex cover constraint, for every edge, the two variables, the two fractional variables, add up to at least 1. And therefore, at least one of those two fractional variables must be greater than or equal to 1/2. The average of those two is greater than or equal to 1/2. So the larger one must be greater than or equal to 1/2. But in particular, that means one of them is at least 1/2, and so one of them gets rounded up to 1, and so for every edge, one of the corresponding x primes is equal to 1. And now claim, let's call this vertex cover C prime. The size of C prime is at most 2 times opt. Why is that? When we round up, what do we do to the objective value? Or the objective value, that sum up there, that represents the size of the vertex cover. You get a 1 for every vertex that's in and a 0 for every vertex that's out. What did we do to that objective value when we rounded? Right. So whenever we rounded up, we at most doubled the value. Whenever we rounded down, well, whatever, we rounded down. Okay, so the worst that we could possibly do is double the objective value, which means that the size of this vertex cover is at most twice the value of the fractional solution. But we already showed that the fractional solution is at most twice the optimum integral solution, the actual size of the minimum vertex cover. So what we have here, again, is a very simple 2-approximation algorithm for minimum vertex cover. Now, we already had a 2-approximation algorithm for minimum vertex cover that was considerably simpler, because this one involves solving a linear programming problem. But now I'm gonna change the problem slightly. I'm gonna change the problem in a way that the dumb algorithm no longer gives you a 2-approximation algorithm. Which is, I'm going to assign every vertex a weight. And now I want not the vertex cover with the minimum number of vertices, but I want the vertex cover with the minimum total weight. So instead of size, I actually want weight. And that is the only thing I need to change. Right, so now I have a 2-approximation algorithm for the weighted minimum vertex cover problem. And the previous algorithm, which just looks at an edge and marks both vertices, doesn't do that. The previous dumb algorithm actually is dumb for this problem. Right? An example of that is sort of interesting counter to the previous example that showed that you don't want to only choose one. All right, so suppose I have a tree like this where the inner vertex has weight 1 and the outer vertices all have weight 10. Then what the stupid algorithm would do is to say, oh, this edge is uncovered, mark both vertices. And so I get a solution with value 11, even though the optimum solution has value 1. Yeah?
When you're rounding up, you're going by, you're increasing the objective by just at the most half, like number half.
I'm going from half to 1, so I'm at most doubling. I'm multiplying by 2 in the worst case. That's where this 2 comes from. This 2 is the reciprocal of this half. So the dumb algorithm that we saw last time would give you an 11 approximation here, or a 101 approximation here, or a Google +1 approximation algorithm here. So you can make the dumb algorithm arbitrarily bad. Right? Whereas the LP rounding algorithm, the exact logic goes through without any changes, and you'll get the 2 approximation algorithm. And in fact, if you ran the LP rounding algorithm for this particular instance, what you would get is just that vertex. Because the only vertex cover that has size at most 2 has to exclude all vertices that have weight more than 2. And so it better give you, it'll actually give you the optimum solution. Okay. So in fact, this is the simplest algorithm known to approximating the minimum weighted vertex cover. It is also, just like the dumb algorithm, 2 is the best approximation algorithm we know. This is also the best approximation algorithm we know for the weighted vertex cover problem. We start with a linear program. We solve it in polynomial time, and then you round the solution. Okay? Any questions? All right. So I'm going to show you. Oh, I'm sorry. Yes.
So, are there any kind of proofs that show that if in an ILP, in the optimum solution of an ILP, the variables which have to be 0 in the LP approximation, they will also be 0? So kind of
In general, no. In general, no. Under certain circumstances, I think you could prove something like that, but it would have to be problem specific.
based on the
What the
objective
question
value.
was.
So the question was, is there a way to, in general, to look at an integer program and say the variables that are 0 in the optimal fractional solution must also be 0 in the optimum integer solution? And no, not necessarily.
So Disclose are an example, right?
Well, the optimum fractional solution is integral in the, yeah.
And the LP relaxation will always have the minimum, like its optimal solution will be less than the optimal solution for the.
Yeah, so this statement here is always going to be true, assuming you're looking at a minimization problem. And the argument is basically, if I look at the picture, the optimum integer solution is feasible. And therefore its value is greater than or equal to the value of the best feasible solution. So it's just definitions. Okay. So I want to show you a different approximation algorithm for the same problem, weighted vertex cover, that gives a worse approximation factor. And the reason I want to show you that, even though it gives you a worse result for the same problem that we've just seen, is that just like the vertex cover things that we've seen already, the greedy algorithm actually generalizes to other problems in a nicer way than the stupid algorithm. The algorithm I'm about to show you, which gives you a log n approximation, generalizes to weighted versions of those more general problems in a much nicer way than this deterministic rounding algorithm gives you. Okay, so I'm going to use exactly the same integer program and with exactly the same LP relaxation. But I'm going to do the rounding differently. Okay, so now I'm going to define x prime of v to be 1 randomly. So The intuition here, I mean, it's a little bit weird, but it's not too totally unnatural. If I solve this linear relaxation of the underlying integer program, the values that I get for the variables are, in some sense, how much this vertex wants to be in the minimum vertex cover. If in the relaxation, I find a vertex whose corresponding variable is 1, then yes, that vertex is in the minimum vertex cover. If I find a vertex whose value is 0, then that vertex definitely is not. But if I find one that's, say, equal to a third, then it's kind of like a third committed to being the vertex cover. And so I'll take that directly as advice. I'll say, okay, great, your probability is a third. I will uniformly at random generate a number between 0 and 1, and if it's less than or equal to a third, I'll accept you into the vertex cover. I'll take this as the probability that the vertex belongs to some subset that I want to choose. Okay. Now, if I look at the expected value of the objective function after I do this rounding, what is it? Well, linearity of expectation gives me this. WV isn't a random variable, it's just a scalar that's given as part of the input. So I can distribute the expected value across the sum by linearity. But this is now the expected value of an indicator variable. So that expected value is equal to the probability that this indicator variable is equal to 1. That's just x stars of v, which is exactly the linear, the optimal fractional value. Right? So I've chosen a set of vertices whose expected size is equal to this fractional, optimal fractional value. That should actually immediately tell you something, which is there's no way that the set of vertices that I've chosen can be a vertex cover. Because the minimum vertex cover is probably going to be bigger than this. So if the expected size of this set is equal to this, then it's not going to be a vertex cover. On the other hand, I can say something about the probability that, what's the probability that UV is covered? I can say something about this. I round this to these indicators x prime. That gives me a set of 0, 1s, which prescribe a subset of vertices. What's the probability that UV is covered? Well, let me write this as 1 minus the probability that xu prime is equal to 0 and xv prime is equal to 0. And let me also mention, by definition, I want to, these variables, I want to flip these bias coins all completely independently so that I can do this split. So this is equal to 1 minus xu star times 1 minus xv star. Okay? Now, what I'd like to be able to say is that this is greater than or equal to something. So that's going to be the same, saying this expression after the initial 1 minus is less than or equal to something. So I want to think, what's the maximum possible value that I could have here? But I have constraints on xu star and xv star coming from here. And so it turns out that if I grind through the math, the the worst case probability that I get over here is when xu star is equal to 1/2 and xv star is equal to 1/2. Right? If the balance is different, I'm going to get a larger product, or sorry, I'm going to get a smaller product, which means I'm going to get a larger final result. So that constraint up at the top, xu plus xv is at least 1, implies that this expression is at least 3/4. Yeah.
So is it actually true that those are independent, though? Because it seems like if...
I've defined them to be independent. The xv stars are probabilities. Given that list of probabilities, I'm now going to do the experiment. And the experiment is, you flip a coin for this vertex, you flip a coin for that vertex, you flip a coin for this vertex. Tell me what the results are.
So like the output of the coins would obviously be independent, but then when you throw it into this function, which is making it 0 or 1 based on probabilities, the x star v's and x star u.
Well, all 1 means is heads and 0 is tails. X star v just tells you the probability of heads versus tails. So I'm defining these to be independent random variables, and here is the distribution.
Okay.
Yeah.
So these constantly probable bias points.
Yes. That's right. The bias coins where x star v is the probability of
But
heads.
this bias is generated. It's coming from this constraint set of. It's constrained
Right.
and they're dependent inside this.
So the values of the probabilities
Are dependent.
are dependent on each other, but having fixed those values, I can now generate independent random variables according to those probabilities. The claim of independence attaches only to the random stuff. And the only thing random in this picture is x prime v. xv star is not random. It is the solution to a linear program, which I'm now going to interpret as a probability. The randomness is all in these variables. So I'm just going to say, I'm going to define a set of mutually independent variables, each of them either 0 or 1. This one has probability 1/2 of being 1. This one has probability 7/8 of being 1, and so on. Yeah.
It's just like I give you 10 bias points, you don't know if they were a solution to a linear program.
Right. Right. I have no idea. But the fact that, it doesn't matter whether the biases were somehow correlated with each other, I'm going to take each coin and flip them in a different room. So it doesn't matter. Yeah. Yes, that's right. So we're not done. We're not done. But remember what we did with the greedy vertex cover algorithm. What we said, the key to the analysis in the greedy vertex cover approximation algorithm said, once we've chosen opt vertices, we've covered at least half of the edges. So let's do that again, and again, and again. And after log n iterations, I know that I've covered everything. So I'm going to do something not exactly the same, but sort of similar in spirit here. I'm going to say, okay, if I run this experiment once, then each edge is going to be covered with probability 3/4. Now, if I run this experiment twice, independently, and take the set generated in experiment 1 and the set generated in experiment 2 and union them together, then the probability that an edge is going to be covered is going to be at least 15/16. I have a probability 1/4 of it being uncovered here. I have a probability 1/4 of being uncovered here. The probability that's uncovered in both is going to be 1/16. Okay? So, run this experiment. Let's say capital N times. Okay, so I'm going to generate x prime 1, x prime 2 up through x prime n. Then now these subscripts are not representing variables, but rather the number of the experiment. So really when I say x prime 1, I mean for each vertex, I'm going to have indicator variables x prime up to vn. Okay, so I'm going to get n subsets. And now, finally, I'm going to let C be the union of, from I equals 1 to n of these individual subsets. Right? Run the experiment once, you mark some of the vertices. Run the experiment again, you mark some of the vertices. You run the experiment again, you mark some of the vertices. Okay? Yeah?
Does that also increase the probability of each node being marked?
Yes, it does. Yes, it does. So, what's the expected size of C? Right, so the expected number of vertices in this vertex cover is at most, by the union bound, the sum from I equals 1 to capital N of the expected size of xi prime. I shouldn't say size here, I should say weight. Sorry. The expected weight of C. Let me fix this. Expected weight of this. But the expected weight of any rounded fractional solution, look at the top of the screen, is opt-twiddle. So this is equal to C times opt-twiddle, which is at most C times opt. All right? So if I run this experiment multiple times, the expected size of the set of vertices that I get is at most, sorry, that shouldn't be C, that should be N, is at most the number of experiments times the optimum value. So if I can somehow, upper bound the number of times I run the experiment, the number of times I run the experiment is the approximation ratio. Okay, so if I could guarantee that by running this experiment 5 times I would always get a vertex cover, then I would have a 5 approximation algorithm. Of course, I can't do that, right? Because I'm just randomly marking things according to these biased random coins. There's always going to be some non-zero probability that an edge is going to be unmarked. But the probability that UV is not covered by C, basically by the logic that we've seen before, is going to be 1/4 to the n. Okay? So now I'm going to play the game that we played sort of at the end of when we were talking about randomized algorithms. It's going to be okay if the algorithm fails some of the time, as long as the probability of failure is small. Okay? So if I set n to be, say, 4 log n, just as an example, then this probability is going to be at most, well, 1/4 to the 4 log n, which, if I've got my math right, is about 1/n to the 4th. Actually, not 1/n to the 8th. Yeah, 1/n to the 8th. Okay, tiny. And so that also means that the probability that C is not a vertex cover, well, this is at most the number of edges divided by n to the 8th, which is at most 1/n to the 6th, because you can't have more than n squared edges in a graph that has n vertices. So in other words, with high probability, we get a vertex cover whose expected size is big O of log n times opt. And if I do this a little bit more carefully, if I just say run the algorithm over and over again until I get a vertex cover. And then figure out what the resulting expected size of the resulting vertex cover is. This high probability bound is going to vanish. So in fact what I could do is just say, if I've run this algorithm for 4 log n iterations and I still don't have a vertex cover, screw it, just every vertex.
That's not a big O log n.
No, it's not big O of log n times opt anymore, but the probability of it happening is so small that it has no effect on the expected size. Right, so this is plus n divided by n over 8. Okay, fine. Or n squared divided by n over 6. I don't really care. All right, this is so small that it doesn't matter. Right, so if I just run this algorithm until it gives me vertex cover, the expected size of that vertex cover is log n times optimal, and where size actually means weight, right? Because I'm doing weighted vertex cover. And I cannot get a log n approximation algorithm by, say, always choosing the vertex with maximum weight, or with minimum weight, or with maximum degree, or doing any kind of greedy thing. Actually just doesn't work. This is, as far as I know, the best approximation algorithm known for weighted set cover. And you still get this expected approximation ratio of log n. I think there's a deterministic version of this where there's not any actual randomness, but it's considerably more complicated, and that extra complication is probably not worth the trouble. Yes?
So, for the algorithm, the rest of the graph, why do we want to restart? I mean, first we have iteration, let's say we find some cover and then we make them, and then run on the rest, even that.
Okay, so this is a very good question. So why do we start over from scratch every time? Because that makes the analysis easy, is the short answer. In practice, what you would actually want to do is to formulate a new integer programming problem that takes into account the vertices that you've already chosen. Compute the linear relaxation of that, which would still assign 1s to the variables that you've already chosen, and round that probabilistically. But if you go through the analysis, you actually still end up with only a log n approximation. In practice, yes, that would be better, but from a theoretical standpoint, you don't actually gain it. As far as I know. I'm sorry?
The long time is getting better.
Yeah, it'll be faster because your linear programs will have fewer variables as you go through succeeding iterations. Okay. Sorry.
How do you get the analysis from 1/4 to the 4 log n to being 1/n?
4 to the log n is n squared. 1 over n squared to the 4th is 1 over the 8th. That's it. It's just math. Okay. So I need to use the last 15 minutes of class to do ISIS. So most of you hopefully have seen these forms already. This is your official report card back to me. There are a couple of things to know about this if you haven't been told this before. One is these pieces of paper only come back to me. They don't actually go to anyone else, and there aren't any copies saved. I get them, they're just to me. But of course, I don't know who you are. Feel free to be as brutally honest as you feel necessary. I don't know who you are. I can't recognize you from your handwriting. What is reported back to the department and to the university for other purposes are your answers to the first 2 questions. Rate the overall instructor's overall teaching effectiveness and rate the overall quality of the course. This is actually used for things like allocating teaching resources. So what I would suggest is fill out the first two questions and then flip over to the back where it asks you for narrative comments, because the narrative comments are by far the most useful thing for me. And then if you have time and you're interested, feel free to fill in the other stuff in the front. I need a volunteer to actually collect all of the forms back in this envelope and drop it off in the mailroom at Siebel. Thank you. Two last things. You must use a number 2 pencil. I realize this is 18th century technology, but if you fill this out with a ballpoint pen, your answers will not count. So if you, the back doesn't matter because I'm the only person who's actually going to see these. But when you fill in the bubbles, you really do need to fill them in with a pencil. So hopefully there are enough pencils to go around. The last thing is, this form asks you to disclose whether you are male or female. Sadly, the gender balance in computer science is skewed enough that it is department policy to ask you not to do that. So half of you please leave it blank, half of you please fill in both, and half of you flip a coin. Other than that, I will see you all on Tuesday. All right, I will be out. I'm not supposed to be in the room, so I'll be out in the hallway. Thanks.